Chapter 7, Part 9, Synthesis of Alkynes. So just like how alkenes can be synthesized by elimination, so can alkynes. If we have a vicinal dibromide, also known as a Vic dibromide, with bromines on neighboring carbons, as long as they also have hydrogens opposite them, you can use two equivalents of sodium azonide to get an alkyne. They do kind of a cross-elimination, where one set is eliminated forming an alkene, and then the next set is eliminated to form the alkyne. If you react in a genital dichloride and take 3 equivalents of sodium azonide in mineral oil and heat, and then follow up with acid, you can get an alkyne. This one's a little more complicated because you're going to be pulling off protons and eliminating one after the other, but you can still make the alkyne. Now let's take a look at the acidity of these terminal alkynes. Recall the pKs of these compounds. The proton on an alkane has a pK of around 50. The proton on an alkene has a pK of around 44. And the proton on the end of an alkyne has a pK of around 25. The relative basicity is going to mirror that. The deprotonated alkane is much more basic than a deprotonated alkyne. But deprotonated alkynes or alkynide anions can be used as nucleophiles. So in this reaction, we're starting off with sodium azonide. That's going to pull off the proton on the end of the alkyne. So the negative charge on the nitrogen picks that up, and after step 1, what you have is an alkynide anion. In step 2, you add in the alkyl halide, and the alkynide anion is able to act as a nucleophile and kick out the bromine. So our final product after step 2 is this. Now make sure that you go back and you count your carbons. There were 2 carbons in this chain off of the cyclohexane, 1, 2. There were 2, 3, 4, 5 carbons in our alkyne. 1, 2, 3, 4, 5. Now these last 2 slides are just an introduction to organic synthesis. We're just going to talk about what a synthesis is. So organic synthesis is the process of building organic molecules from simpler precursors. Usually this is done because the compound that you need is not available naturally. So any multi-step reaction essentially is a synthesis. So natural products can save lives, but usually they are impossible to harvest from their natural source in the required amounts, or they need adjustments in order to reach their full potential. There are 2 different types of reactions, really, in all of organic chemistry, essentially, that you use in organic synthesis. The first one is the conversion of one functional group into another, and the other type of reaction is to form carbon-carbon bonds. These are the types of reactions that you'll use when you're trying to do an organic synthesis problem. Synthesis can be done in one step. That's just not a very good problem exactly for practice or for a quiz or an exam, or very many steps depending on the target molecule. So when you're working through a synthesis problem, your first step should be to count the carbons in your target product and also in your starting material or starting materials. Do we need to add carbons? Do we need to lose carbons? How many? Will we need multiple equivalents of the starting material? Then compare the functional groups present in the product versus those in the starting materials. Next, lay out all of the possibilities for making that final functional group. Usually the final functional group is a little more interesting, and you probably only know 1 or 2 ways that you can make it, whereas the starting materials are going to be very malleable. You're going to be able to do tons of reactions with them. So working the problem backwards can actually be really helpful so that you can figure out what maybe your last 2 or 3 steps are. Then you can go back to the beginning and work towards that. So working backwards, determine possible precursors and the reagents that you need to get there.